Good day everyone. Today we are presenting our machine learning project title, Custom Pothole Detection and Segmentation using YOLO. Our project focuses on using artificial intelligence to automatically detect pothole from road video footage. Instead of relying on the manual road inspection, we build a complete machine learning pipeline that can identify pothole, segment the shape, and show the detection result using on videos. The full workflow starts with the dataset from Roboflow, followed by annotation and model training using YOLO. After training, we export model into ONNX format so it can be used outside the trainings. Finally, we run the model through a web-based GPU inference system and demonstrate a result on the road footage. Our team members are me, Naim, Loh Yin Chuan, and Saleh. Each of us handle one major part of the project, but the whole system works as one complete pipeline. Today, we will walk you through the problem, dataset preparation, training process, model comparison, deployment, and final recommendation. This slide shows how we divide the project responsible among the three members. Me is responsible for the problem statement and dataset development. This including understand the road inspection problem, preparing the Roboflow projects, setting annotation rules, creating the train, validation, and test split, and adding null image to improve model robustness. Loh Yin Chuan is responsible for model engineering section. This includes selecting the YOLO model, setting up Google Colab GPU environment, choosing the train configuration, monitoring training logs, and evaluating model using performance metrics. And lastly, Saleh, he is responsible for deployment section. This includes exporting the train model of ONNX, running the model inside the web GPU inference apps, handling counting logic, and presenting a final recommendation. Even though we divide the work by role, every member understands the workflow from the start to finish. This is important because machine learning projects are connected end-to-end. A dataset decision can affect training result, and training result can affect deployment performance. So, our presentation is structured not only by team roles, but also by the natural flow of real machine learning projects. This roadmap shows how our presentation matches the assignment requirement. We began with the problem statement and relevance. Then we move into dataset development and annotation. After that, we explain the model architecture and training setup, followed by experimental result and model comparison. Finally, we discuss deployment, demo, result, recommendation, and conclusion. The key storyline of our project is this. Our first model performed reasonably well on familiar training style image, but it struggled when tested on a new road video. It missed some pothole, detects shadow and wet patches as potholes, and sometimes produce inaccurate masks. This led us to an important machine learning lesson. The issue was not only model architecture. The bigger issue was dataset generalization. The model had not seen enough examples of normal road, shadows, cracks, and other confusing road surface. So we improved the dataset by adding null or background road image. These are images with no pothole labels. This helped the model look not only what pothole looks like, but also what a normal road looks like. The dataset improvement became the main turning point in our project. Now, let's move into the problem statement. Pothole is commonly road defect that can damage our vehicle, reduce driving comfort, and create safety risks for road users. Traditionally, pothole inspection is done manually either by road maintenance teams or through report from the public. The problem is that the manual inspection is too slow, inconsistent, and difficult to scale, especially when long road network need to be monitored. Our project goal is to train custom YOLO model that can detect and segment pothole from recorded road footage. The system is expected to identify road defect automatically, support maintenance prioritization, and demonstrate a deployment machine learning pipeline. The output is not just simple classification. We want the system to show pothole box or mask, confidence score, frame rate, and the comparison between two YOLO models. In simple terms, this project asks, can we use a trained computer vision model to support faster, more consistent road inspection? This is why pothole detection is a suitable machine learning problem. It is visual, practical, and has clear real-world application. This slide highlights the main challenge we faced during the projects. At first, our model worked quite well on familiar image, especially images that look similar to the training dataset. However, when we test in a new environment road video, the performance drops. We observed three main problems. First, the model missed real pothole, especially when light, road texture, or camera angle was different from the trained image. Second, some detection had poor localization. This means the box or segmentation mask did not accurately cover the pothole area. Third, the model produced false positive. It sometimes detects tree, shadows, road crack, wet patches, and dark road region as a pothole. This is very important discovery because it showed that the problem was not simply use a bigger model. A bigger model does not automatically solve poor generalization. The real issue was the training data did not represent enough road condition. The model had learned a shortcut. Dark and irregular road area may be potholes, but in real road footage, many dark regions are not potholes. So the key lesson from this slide is that machine learning model is only as good as the data it's learned from. The root cause of the problem was what we call pothole-only bias. In the first version of the dataset, most images contained pothole. This means the model was mainly exposed to positive example. It learned how potholes look, but it did not learn enough about what normal road surface look like. As a result, when the model saw a new road surface, it was more likely to assume that something dark or uneven must be a pothole. Before adding null image, the model saw mostly pothole image and had weak understanding of clean road background. After adding null image, the model saw both pothole and normal roads. This allowed it to learn positive case and background case. It is important to clarify that null is not a new case. We did not create a class called normal road. The class list remains one class only, a pothole. Null image simply means image with no pothole annotation. Their label files are empty. This good road image acts as a background training data. This directly targets our false positive problem because the model learns that shadow, cracks, wet surface, and normal road texture should not always be detected as pothole. This is our final dataset strategy. Our final dataset contains 3,785 total images. From this, 2,718 images, around 72%, were used for training. 709 images, or 90%, were used for validation. The remaining 358 images, or 9%, were used for testing. The dataset includes pothole image with segmentation mask or bounding box. It also includes null good road image with no pothole labels. Most importantly, we include hard negative example. These are difficult background images that may confuse the model, such as shadow, crack, wet patches, and dark road texture. The purpose of adding this image is to reduce the behavior where the model thinks everything dark is a pothole. This improves test time precision, especially on unseen road footage. It also makes a validation and test set more realistic because real road video do not contain pothole in every frame. So our dataset strategy is not just about increasing the number of the image, it is about improving the quality and variety of the learning example. This slide explains how we split the dataset. The training set we use to teach the model. The validation is used during training to monitor performance and tune the image. And the test is used after training to evaluate how well the final model performs. In our project, the split must test two things: pothole detection and false positive behavior on no pothole roads. A very important rule is to keep the final demonstration video completely outside the training dataset. If we train on frames that we are too similar to the demo video, the result may look good, but it would not be a fair test. This is called data leakage. We also avoid placing near duplicate frames from the same video into training, validation, and test set at the same time. If similar frames appear in every split, the model may appear more accurate than it really is. To validate generalization, our validation and test set must include different roads, different light, and no pothole frames. This also to ensure that both YOLO models are evaluated fairly using the same split and video settings. A good dataset quality depends not only on the image, but also on the annotation. For pothole segmentation, inconsistent mask or box can cause poor localization. If the label does not tightly match the pothole, the model may learn inaccurate boundaries. We apply several quality control. First, we use one class only pothole. This is to prevent the model from learning a wrong class such as null or good roads. Second, we use tight pothole masks or boxes to improve detection and segmentation quality. Third, null images have empty labels. This teaches the model background information without creating any false class. Fourth, we remove duplicate or blurry frames to reduce bias and noisy examples. And finally, we review hard negatives such as shadow, cracks, and wet patches. This is important because these are the exact things that cause fall detection in our first test. In simple terms, annotation quality connects directly to our project challenge. Better labels and better background example help reduce false positive and improve mask accuracy on unseen videos. This is our end-to-end machine learning pipeline. The first step is dataset collection, where we gather pothole and road image. The second step is annotation and split, where potholes are labeled and the data is divided into training, validation, and testing set. The third step is YOLO training, where the model learns to detect and segment pothole. The fourth step is ONNX export. This is important because it allows the trained model to be used outside the training notebook. The fifth step is web GPU inference, where the exported model runs inside our web application. And the final step is recorded video demo, where we show the model detecting pothole from real road footage. The main message of this slide is that our project is not just training experiment, it is a complete machine learning workflow from label data all the way to real video inference. Let's complete the problem and dataset section. Next, we move from the dataset preparation into the model engineering section, where Luis will explain which YOLO model were selected, how we are trained, and how their performance was evaluated. That's all from me. Thank you.
Thank you, Naim. Hi everyone, I am Loin Chuan and I will now take over for the modeling section. We actually compare two YOLO segmentation models. The first one is the model A, which is YOLO V8 segmentation. It is the larger accuracy-oriented model at 27.2 million parameters, while model B is the YOLO 26S, which is a newer, lighter, and more efficient model at 10.4 million parameters. It is about 2.6 times smaller compared to YOLO V8M. We deliberately picked one proven heavyweight and one lightweight model so we could compare them fairly on accuracy, false positive, speed, and size. Both use the same train validation and test split and the same 640 pixel or an NX export, so any differences come from the model, not the setup. Okay, now let's look into the training environment. Actually, both models were trained on an NVIDIA A100 40GB GPU in Google Colab using PyTorch with CUDA at 960 pixel image size, then exported to ONNX for deployment. The high memory GPU let us train at a larger image size, which mattered here because many potholes are small and low contrast, and more pixels give the model more detail to work with. For the training configuration, actually both models were trained under identical setting, which are 100 epoch, 960 image size, batch size 16, early stopping patient of 30, and mosaic mix up and copy and paste augmentation to improve robustness. Keeping every setting the same for both models is what makes the latter comparison fair. So any performance differences is down to the architecture, not the training recipe. Now let's talk about the evaluation metrics. We evaluate both models with precision recall MAP at 0.5, MAP at 0.5 to 0.95, and different speeds. In our problem, both precision and recall matter. This is because a missed pothole is a safety risk and a false positive on a shadow or wet patch, waste, and inspection. We keep these two in mind, which are the precision and the recall, because the differences between them is exactly what decide our final model choice later. Let's talk about the training result. These are the validation metrics from the 640 pixel deployment models. YOLO V8M leashes box MAP 0.863 and mass MAP 0.855 with precision 0.885 and recall 0.854. YOLO 26S leashes box MAP 0.826 and mass MAP 0.827 with precision 0.82 and recall 0.927. So on paper, the YOLO V8M is a few percent higher on MAP, while the YOLO 26S is about 27% faster, which is 4.5 versus 6.2 milliseconds, and it is about 2.6 times smaller. But notice the numbers are close, and each model lead on different measures. These offline scores are only the starting point. What we really decide it is how the model behave on real road video, which will be shown by Charlie shortly. These are the precision recall curve for both model overlaid. YOLO V8M reaches box MAP 0.957 and mass MAP 0.955, while YOLO 26S reaches 0.942 and 0.94. Both models achieve very similar results. Besides that, both models hold precision near 1.0 until about 0.8 recall. So on this validation set, both models are strong and the curve almost sit on top of each other. The F1 peaks give us our deployment confidence threshold, which is about 0.45 for the YOLO V8M and 0.4 for the YOLO 26S. The takeaway is that the two models are nearly identical on this offline curve, and the real separation only appear on the deployment video. These are the confusion matrices on the test set. YOLO V8M records 2063 true positive, 409 false positive, and 119 miss. YOLO 26S record 2022 true positive, 443 false positive, and 160 miss. So in raw count, the YOLO V8M records slightly more detection and slightly fewer misses. But raw count alone can be misleading because a higher count includes both correct detection and false positive. Whether those extra detection are actually correct is the real question. And that is exactly what we examine on the deployment video in the next few slides, which will be explained by Salih. So to summarize the comparison, the YOLO V8M has higher recall, so it fires on more candidate regions, and it has a slight edge on offline MAP. However, the YOLO 26S is faster and 2.6 times smaller, making it well suited to real-time or edge deployment. At this stage, neither is simply better because each model leads on different measures. The deciding factor is how cleanly each one performs on real-world video. Before concluding my presentation, I would like to mention how we address the main challenge in developing both models. Before adding now, with a pothole-heavy dataset, the model rarely saw a clean road, so it over-predicted and flagged shadow and wet patches as pothole. After adding images of a road with now and background, the model learned what a normal road looks like. The clean road is now the background, not pothole. That single change is what cut our false positive. The key point is that we fix it by improving the data, not by changing the model.
This table ties each failure to a cause and a fix. Mix pothole to more varied data and larger input size of target boxes to tighter annotation. False positive to null and hide negative. Repeated counting to tracking. The important distinction, detection quality has to improve before tracking. If the detector is still wrong, the tracker just follow its mistake. We deploy a web apps at potholeiteratechnologies.com so we can run inference remotely and show a live demo. You upload road footage, pick the model, it just confident and IOU, and it's return the process video with marks, confident and FPS. ONNX export is what lets the model run outside the training notebook. Detection and counting are related but different. YOLO detect pothole per frame and NMS, controlled by the IOU threshold. IOU threshold remove duplicate boxes with a frame, but NMS is not a tracking. To count pothole once across a video, we track them across frame and count unique IDs. Our app uses an IOU tracker, ByteTrack or BOT sort are the production grade upgrade. Here is the real frame from our live benchmark apps with both models running on the same footage. On the left is YOLO 8M and on the right YOLO 26S. Notice that YOLO 26S produces a cleaner, tighter mask with fewer false positives on shadow and wet patches and run faster, 8.4 milliseconds versus 10.9 milliseconds. We use the same video and the same confidence and IU for both. So the comparison is fair. This real-world behavior is the main reason we recommend 26S. Issue 1. YOLO 8M detect more pothole in the video, so isn't it better? The key is the difference between recall and precision. Recall is how many of the real pothole the model finds precision is how many of its detections are actually correct. A high detection count only means higher recall. It doesn't mean the detections are right. Look at the frame. YOLO-IM paint large area of wet road or as pothole, while YOLO-26S mark only the real ones. So YOLO-IM's high count is mostly extra false positive. This matters because our entire project was about cutting false positive on shadow and wet patches. And for a real inspection tools, every false pothole is a wasted repair crew dispatch. So precision is what protects real world costs, and YOLO-26S has a better precision. Issue 2, if YOLO-26 is better, why? It's confidence not higher. Because confidence measures how sure the model is about a detection. No, not whether the detection is correct. A model can be confidently wrong. YOLO-8M report a wet patch as a pothole at a high confidence. The number is high, but the prediction is false. And in practice, the two models are basically tied on confidence around 71 to 72%, a difference too small to matter. So, confidence cannot decide which model is better. What we actually judge on is mask quality. Does the mask fit the real pothole, the false positive rate, and inference speed? On all three, YOLO-26S is stronger on a real road video, and those are the properties that decide if the tool is usable in the field. Being honest about limitation, performance can still shift under night, rain, camera, shake, or unusual surfaces. Near term, we add more hard, negative, and target domain video, and we train. Longer term, we add stable tracking and counting and use mask area to estimate pothole severity. Our recommendation, we deploy YOLO-26 segmentation. On the offline test set, YOLO-8M has a slight edge on a recall and MAP. But on the real inspection video, which is what actually matters, YOLO-26S perform better. Cleaner and tighter mask, fewer false positives on shadow and wet patches, smoother and faster playback, and more stable direction. This is a key insight. The model that leads on benchmark number is not always the best in deployment. YOLO-26S generalized better to real road video, so it is our pick. We keep YOLO-8M as the alternative when maximum offline accuracy outweighs speed. To conclude, we built a complete YOLO pothole detection and segmentation pipeline. The key difficulty was poor generalization on new road video, which we solved by adding a null background image to cut false positive. We compare YOLO-8M and YOLO-26 on the same footage and recommend YOLO-26 as segmentation. It generalized better to real road video with cleaner masks and fewer false positives, even though YOLO-8M has a slight edge on offline benchmark number. Thank you. We are happy to take a question, and the live demo is at potholealteratechnology.com.
Hello everyone. Now I will demonstrate how we prepare the dataset before training the YOLO model. In any computer vision projects, the model performance depends strongly on the dataset quality. If the image labels are poor, inconsistent, or not representative of real-world conditions, the model may detect potholes wrongly or fail when tested on a new video. So we start with selecting a project, make a new folder for it. So go inside and select a new project. So we'll define the project name, and then in these cases we're going to use the instance segmentation. This allows the model to locate each pothole and draw masks around it, exact shape, instead of only placing a rectangular bounding box. This is useful because potholes have irregular shapes and the mask can better represent the real damaged road area. So I'm going to create public projects. Here we have two options, select file and select folder. So select file is used when we want to upload the individual image, and select folder is used when the dataset is already organized into a folder. So I'm going to select folder. to the target file, and then I'm going to upload it. Click upload. So we can also add a similar image recommended by YOLO itself. So in this case, I'm going to select this one, and click add. It's going to transfer into these boxes, this area. Click save and continue. Once complete, we're going to transfer to these pages and assign an image. So an assigned image is image that have already been uploaded but not yet included in the train validation or test set before training this. So I'm going to choose a label for myself. This step allows us to choose how the image will be labeled, because labeling gives us better control over annotation quality. Start annotation. So another important part of our dataset preparation is adding null image. This is null. I'm going to define this as null. Why we use this null image? Because the model will learn that not every dark road region is a pothole. This helps to reduce fault detection during the real video interference. I'm going to set null shown in here. Now, because there's no pothole. Now, I'm going to use this tool, Smart Select, to select this pothole area. Finish, enter, and define this as a pothole. So enter. Next image. So have these two polygon. So the image can look better. Next, something like this. Next. So I'm going to fast forward the video. Add this 90 image to dataset. 70, 20, and 10 image. Okay. So there you go. We have test, train, and validation. In the version page, we actually have complete step 1 and step 2. Step 1 is where we source the image, and then step 2, we're going to split the dataset into 3. So we're going to rebalance our dataset to train, validate, and test. Going to 7, 32, 31. This is the balance. But in our actual project, we set 70, 30, and 10. In this situation, we only use select rebalance with 19 datasets numbers. So we going to save it. Continue to step 3. And this is pre-processing. YOLO pre-processing is a step where image and label are prepared before training. The image are resized to a fixed input value, pixel value, and normalized. In here, we set to 960 times 960. Click to apply. Random sample. Put everything in 100. And then we click continue. Next is augmentation step. Data augmentations means creating variation of original image. For example, the image can be rotated, brightened, darkened, crop, scale, and slightly change color. So we're going to just rotate. Okay. Add more augmentation. Share. Apply. And blur. Apply. So now we have something here. Then we click to continue. So now we're going to create additional image. Here, how it's calculated. So we're going to just create. So now the dataset is ready. We're going to click download dataset, use zips, and choose what is the model you use. Here we have 11, 26, 8, and I'm going to download 11. Continue. After downloading the dataset from Roboflow, the zip contains complete YOLO dataset. So we have 3 files in here. The train folder is used to teach the model. The valid folder is used to monitor training performance, and the test folder is used for final evaluation. Data YAML is important because it tells YOLO that the dataset path and the class name, which in our case is pothole. Then inside of the folder, there's an image and a labels folder. The label folder contains the annotation file of each image. Each image has matching text file that tells YOLO objects, class, and the pothole location. This is what the data has been written. That's all from my side. Thank you.
Hi, I'm LabelImg, and right now I will present how we train the models. This is our training notebook in Google Colab, the IoT era AI solution machine learning pipeline. It covers pothole instance segmentation trained at image 960 with the dataset and results stored on Google Drive. You will notice 3 models listed here. We trained YOLO 11 large segmentation as well, but didn't pick it for our final comparison. It is the heaviest of the 3. And once we had YOLO V8M as our accuracy model and YOLO 26S as our lightweight one, 11 large set only in between, slower and larger than 8M without giving us better result to justify it. So we dropped it and kept a clean contrast between accuracy and efficiency. You will see it in the notebook, but it is not in our recommendation. So before the notebook, let's go into the Google Drive. Here is how our project is organized on Google Drive. Under My Drive, Machine Learning Assignment, the 2 main folders are datasets, which hold all our images and labels and result, where every training run is saved and each run folder contains its own weights, including the exported or an NX model for deployment. So inside the dataset folder, you can see the 3 split folder, train, valid, and test, and also the data.yml file that tells YOLO where each split is and what the class name are. This is the exact path the notebook read from My Drive, Machine Learning Assignment, and Dataset. And inside the folder of the result, each model has its own run folder. The 2 that matter folders are YOLO V8M and also YOLO 26S, our 2 final model. You can also see the older YOLO 11L run that we trained but we didn't select. If I open the YOLO 26S weight folder, you can see the best.onx file and also the best.pt file. The best. ONX file will be used for deployment. So now look into our training on environment in Google Colab. So before runtime, we have to check our GPU. So you can click here and then change runtime. Make sure you choose the A100 GPU. And once it is connected, it will be show up here. After we connected to the GPU, we have to do the GPU check. So cell 1 confirm our hardware. The resources panel show we are on a collapsed GPU backend and the output confirm an NVIDIA A100 with 40 gigabytes running CUDA 13 and PyTorch 2.11. This is what let us train at image size 960 with Bash 16. After completed the GPU check, we have to install the dependency. So in cell 2, we install the authoritative, which is the library that gives us the YOLO models. Once it's finished, it prints the version numbers confirming the library is ready. In cell number 3, we mount our Google Drive into the notebook. This is how Google Colab read our dataset and write the result back. After authorizing, it print drive mounted, so everything in our machine learning assignment folder is now accessible. Cell 4 is the only cell that we edit between us. It set the dataset and result path, the run name, and the main hyperparameters. So yeah, the 100 epoch image size 960 and batch size 16 all setting here. And also the path to the Google Drive, just now I have shown in Google Drive, how to access to the folder. These three switches control which model train. So you can see here V8 false, V11 false, and V26 true. Right now, only YOLO 26S is set to true because the other model were trained in earlier round. So we don't retrain them every time. The output confirm that the path and the image count 2,688 images for training and 709 images for validation, 358 images for testing. So let's look into cell 5. Cell 5 actually does two things. First, it clears any store label cache. So the model always read our latest label and never an updated version. Then it copy the whole dataset from drive folder, the same dataset folder I showed earlier, onto Colab, local disk and content dataset. Because training directly off drive is really slow. When it is done, it prints the final count of images and label each split, confirming everything copied correctly. For cell 6, actually cell 6 rewrite the data.yaml file, the one we saw inside the dataset folder. So its path point to the local copy, then verifies the dataset. The output conform our single class pothole and print the train, validation, and test path, so we know the data is wired up correctly before any training start. Now let's talk about the training configuration. Cell 7 built the training configuration shared by every model, which is what keep the comparison fair. A few key setting: cosine learning rate, schedule with early stopping, and IOU threshold of 0.7 for validation, and this augmentation block, color jitter, rotation, scaling, flips, and mosaic. That augmentation is important because it helps the model generalize the root video it hasn't seen before, which directly tackle the domain gap problem where a model trained on one set of root fail on new footage. The output just confirm the configuration is ready. Cell 8 and 9 are the training and validation for YOLO V8M segmentation, our accuracy-oriented model. So we train M in an earlier round. We shut this off here and just print skip. We don't retrain it for this demo. Its real results are saved in our drive result folder under YOLO V8M, which I will open now. This is the result for the V8M. So here are the 8M actual output from that run, the CSV file, and the training curve, everything is here. So cell 9 is also where 8M was exported to ONNX, which is the file Saleh uses for deployment later. The MAP numbers from here are what fit into our results slide. Cell 10 and 11 are the YOLO 11L segmentation model I mentioned at the start. As we decided this is the one we didn't carry into our final comparison, so we leave it, switch it off, and move on. So now we go to cell number 12. Cell 12 plot the training curve for the 8M and 11L runs. Because those are switched off, we didn't do the training for 8M and 11 for this demonstration. It wouldn't draw anything live. But the safe curve are the training curve PNG file inside each model result folder, which I have shown just now. Cell 13 built a comparison table by validating each active model on the test set. Since we are only running 26S for this demonstration, it print the 26S row. So, and this is the result. So, and the full side-by-side against YOLO 8M is in our previous slide where we put both model real number together. So now dive deeper into the YOLO 26S training. Cell 14 train YOLO 26S, our lightweight model. This is the run we did for this demonstration. The key advantage noted right in the code is that YOLO 26S handle known maximum suppression internally. So there's no separate post-processing step that give faster inference. Exactly what we want for real-time video. It uses the same training configuration as YOLO 8M, which is what make the comparison fair. Here you can see the full 100 epochs run completed, and here you can see the 100 epochs completed in 2.1 hour by using the A100 GPU. And this is the result, and everything is saved inside the Google Drive folder. After completing the training, in cell 15, we validate YOLO 26S on the test set and export it to ONNX file. The export convert the train best.pt file into a best.onnx file directly here in Collabs. So the converted file is actually saved inside the folder that I've shown inside the Google Drive, and then Saleh will be used to deploy at the web apps. So no PyTorch and no further conversion needed. So here you can see the export succeeded. Finally, cell 16 plot YOLO 26S training curve. Same format as before, the smooth downward loss and rising MAP confirm the model train cleanly. So yeah, this is the result. So to summarize the model training, both models were trained on the same dataset with the same configuration, evaluated on the same head-up test set, and exported to ONNX file. YOLO V8M as our accuracy model, while YOLO 26S as our lightweight one. The detailed comparison we already explained in the presentation slide, and the final recommendation also presented by Saleh. So that's all for my presentation and demonstration. Thank you.
This is our AI road condition monitoring system developed using the Ta'ant framework by Ayutera AI solution. The system performs real-time pothole segmentation On dashcam footage using two custom trained YOLO 8M and YOLO 26 segmentation, both fine-tuned on a merged pothole dataset with hard negative mining. On the half left sidebar, we have full control over detection parameter, confidence threshold at 0.5, filter weak detection, IOU NMS threshold at 0.5, control overlapping mask suppression. For the playback speed, we have, for the playback setting, we have playback speed, frame delay, and the process every end frame slider allow real-time balancing between smoothness and inference frequency. Display mode, we support single model for focus analysis and side-by-side comparison for direct model benchmarking. For the counting mode, the byte track toggle enable our custom IOU-based pothole tracker detection. Persisting fewer than 3 frames are discarded as noise, filtering false positive from shadow and vegetation. Visualization, bounding box label, and confidence score are individually toggleable. For segmentation, we prefer mask only, cleaner, and more accuracy. For benchmark, the sidebar displays static evaluation metric map at 50 inference time, parameter, and G-flop for both model. Now we will start for the single model demo. Starting with single model mode, using YOLO 26x segmentation, which is our fastest model at 8.5 millisecond inference, 10.5 million parameter, 34.5 G-flop. We can notice that the blue segmentation masks correctly identifying pothole boundary on this muddy road. We can see that the YOLO 26 achieved at around 23.7 FPS on the RTX 5070 Ti. So now we will do a side-by-side comparison. Now we're switching to side-by-side mode, which is model A is YOLO 8M segmentation with 27.2 million parameter, while model B is a YOLO 26 segmentation with NMS built into the model architecture, no post-processing overhead. We can notice that the YOLO 8M on the left, the entire road surface is flooded with the blue mask. The model is over-segmenting, misclassifying the wet muddy road texture as pothole. This is false positive flooding issue common in the model trained without a sufficient hard negative. For YOLO 26 on the right, show the far superior specificity, correctly identifying only distinct pothole boundary, ignoring the surrounding wet route surface. YOLO 8M counted 63 detection versus 54 for YOLO 26. However, YOLO 8M high count is due to over segmentation, not better accuracy. YOLO 26S is actually performing more reliably here. This evaluation revealed a critical insight. High benchmark MAP does not guarantee better real-world performance. YOLO 8M achieved 0.855 meg on our test set but over-segment on muddy condition. YOLO 26 at 0.827 meg generalized significantly better to unseen road environment, making it recommended model for real-world deployment. That's it for demo for this project. Thank you.